Hello students. Today we'll be looking at the eighth assignment of IBTL, that is security best practices. So under this assignment, we need to cover two sections. The first one is analyzing common security vulnerabilities in smart contracts, and the second is to implement best practices to secure a smart contract. So before starting with the assignment, we need to understand what are the common security vulnerabilities in the smart contract and then implementing best practices. Let's look at first the concept. So the common security vulnerabilities in smart contracts, we'll be discussing two: the reentrancy attack and integer overflow and underflow attack. Beginning with what is reentrancy? So it's a type of attack that occurs in smart contracts that allows untrusted external code to be executed within the contract. It's a way of exploiting a vulnerability in a smart contract, which basically allows an attacker to repeatedly call a function in the contract, which makes an infinite loop and potentially stealing funds from the contract. Looking at a very simple example of reentrancy, there can be a scenario that allows users to deposit funds and then withdraw those funds later. So suppose the contract doesn't have proper security check for reentrancy. In that case, what the attacker can do, it can call the deposit function multiple times in a row before calling the withdraw function, and hence effectively stealing funds from the contract. So there are different ways of preventing reentrancy, as we have to also implement the security best practices for reentrancy. And there are different ways of doing it, using a mutex function or a mutual exclusion function, or lock to prevent multiple calls to the same function from occurring at the same time. Another way is to use a guard condition. So basically, in this assignment, we are going to use the Open Zeppelin's reentrancy guard to prevent the contract from falling victim to reentrancy. So here is a simple example for reentrancy attack. The standard reentrancy is when attacker is repeatedly calling a function in a contract, making an infinite loop, and then potentially stealing funds. So a user interacts with a vulnerable smart contract to deposit funds. So what the malicious contract will do is it will repeatedly call the deposit function of the vulnerable smart contract, depositing funds into the attacker's own account. The malicious contract then calls the withdrawal function of the vulnerable smart contract for withdrawing the deposited funds. The loophole here is that the deposit function of the vulnerable smart contract is not properly protected or secured against reentrancy. So as a result of this, the attacker is able to repeatedly call the deposit function before calling the withdraw function, and thus effectively stealing funds from the contract. So let's look at a diagram which will help us understand this scenario better. So there's a contract A and contract B. Contract A is the vulnerable smart contract, which we will be writing in our assignment. So this vulnerable smart contract has a check balance function, send fund function, and update balance function. Contract B is a malicious contract, which has fallback functions written, which will fall back into the contract A before it is done updating the balances. And contract A, since it is not updating the balance, it will go into an infinite loop and go on sending funds to the malicious contract. So in this assignment, we are going to write the vulnerable contract, okay, not the malicious contract. So we are going to write the vulnerable contract and look at situations by which it can be exploited to reentrancy, and then we'll implement a secure smart contract which will be safe against reentrancy attack. So let's first have a look at a contract that can be vulnerable to reentrancy, understanding the reason why it can be. So we have written a contract reentrancy with a mapping. The name of the mapping is balance, and we are mapping address to unsigned integer, which means that we need to keep a track of what balances each address is holding. Then we have written a function deposit, which we make it as payable. So it needs to be mentioned that whenever you're writing functions which deal with either deposit or withdrawing of funds, that should be marked as payable. Okay. So payable is a keyword that is used for functions that are dealing with funds. So for deposit function, whatever the user is passing as a value, we are going to just update the balance with that value by adding that new balance into the existing balance. Function withdraw, which is going to be used for withdrawing funds. So here inside this, we have written a require condition that the balance of message dot sender should be greater than the withdrawing balance. Obviously, then only you can withdraw funds. So if this required condition is true, then only the transfer would occur, and we'll update the new balance by subtracting that amount from the existing balance. Now this, why we are calling this as a vulnerable smart contract to reentrancy is there is no check put on the withdrawal function. It is just checking whether that amount is lesser than the balance and just allowing it to withdraw. So if there is a malicious actor who goes on calling this function in an infinite loop, this contract would be drained out of funds. So that is why we are calling it as a vulnerable smart contract. Now, this is a vulnerable contract. We'll look at how to prevent or how to write a secure smart contract. So in order to implement best practices to secure a smart contract against reentrancy, we are going to use the Open Zeppelin's reentrancy guard. So this is a contract utility that helps protect the functions from reentrancy, which is a very common vulnerability in Ethereum smart contracts. So we'll directly look at this security best practices in the remix itself. Okay, so here, in order to implement secure best practices for reentrancy, we have imported a library which is Open Zeppelin's reentrancy guard. So this reentrancy guard is a pre-written code which protects the smart contract from reentrancy. So we need to import this file. Open Zeppelin is a safe library which provides a lot of support for pre-written codes that can be incorporated with our smart contract. So now we are writing our own contract, that is secure wallet. Is reentrancy guard, which means that this secure wallet is going to use reentrancy guard. Okay. Again, we have written the same mapping, that is, we are just maintaining a mapping balances which will map what are the balances stored with different addresses. Then we are writing the deposit function in the same way that we have just now discussed. Whatever is the value passed, we are updating the balance with that value. Now, while writing the withdraw function, because this is the place where the malicious actor can intervene and drain out funds from a smart contract. So we have imposed the security check here. How? So we have written the function withdraw with an amount that is passed by the user. We have made this payable, yes, because it is going to deal with funds. And we have used a modifier non-reentrant. Okay. Now this non-reentrant is a modifier. Okay. That is written inside reentrancy guard. So this prevents a contract from calling itself directly or indirectly, and hence will not allow it to be called in an infinite time. and thus we would be able to prevent this contract from getting victim to reentrancy. So that is an important point, that we are using the non-reentrant modifier from the open Zeppelin's reentrancy guard. Again, we are checking the same required condition, that the amount should be lesser than the balance, current balance, and otherwise we will just display an error message, insufficient balance. If this is true, we are updating the balance, that is deducting the amount and transferring the amount to the dedicated address. And at last, we have written a contract get balance just to display the balance of the account. So the main focus here is what is reentrancy guard, opens Zeppelin's reentrancy guard, which provides a modifier non-reentrant, by which we can prevent the function from getting called uh, in an infinite loop kind of a situation, and thus preventing reentrance. Now let's compile this. Okay, let's deploy. I'll be using the Remix VM Canton to deploy this. Let's deploy this. So it's deployed here. Let's look at the deployed contract here. Now, in order to deposit, let's say I want to deposit certain amount, I can just go to this value tab and deposit certain values. You can change this to Ether. So I'm trying to deposit 2 Ethers here. So let's say deposit. Okay. So you can see that this amount has been deposited here. Okay. Now let's go to withdraw. Okay. So let me just withdraw the entire amount that I just deposited. So let's say 2i. Okay, no, here we are directly providing the value for withdraw here only. So let's say withdraw and then get the balance. So it is updating the balance. Okay. So which means that the deposit and withdraw functions are working fine, right? So you can also get the balances of different addresses by pasting it here anyways. But that is fine. That is getting displayed here also. So let me just show you that way also. So let's copy this account address and put it in the balance tab and get the balance. Yes. So this has updated the balance here. Okay. So we in this assignment, we are not writing the malicious contract or the attacker contract. We are just writing the main contract and making it secure against reentrancy by using the Open Zeppelin's reentrancy guard. Thank you.